So, by now we have developed several techniques and we have understood how to deal with rigid body motion if one point is fixed and it is rotation about that point. Our central equation is torque is equal to dl dt, where L is the angular momentum, and that is true for inertial frame of reference. So, we can use any axis system to describe the body. If it is inertial frame, it is good, fine, you can write your equations, but many times it is simpler to use axis system which are rotating with respect to the inertial frame of reference. So, if you use the rotating frame of reference, then this dl dt inertial is equal to, in the inertial frame, is equal to dl dt in the rotating frame and plus omega cross L. Omega is the angular velocity at that instant. This equation works. And then this rotating system can also be of two types: fixed with the body is rotating, this frame is rotating, and this frame is fixed in the body. This is one possible choice. Another possible choice is, yes, it is a rotating frame, but the axes are not fixed in the body. They are not fixed in the inertial frame and they are also not fixed in the body. That is also possible, and sometimes that is more useful. So, we will be using that. Sometimes it is, this is easier. So, we will be using this. So, fixed with the body and not fixed with the body. So, depending on the situation, we can use inertial frame or a rotating frame. In the rotating frame, we can either use a frame which is fixed with the body, which rotates with the body, and with respect to the body the frame is fixed, or we can have a rotating frame, but the body is not fixed in that frame also. So, that can also be used. If you are using this, if you are choosing the frame which is fixed with the body, or even in this case also, if the axes are, it is a other issue, if the axes are also principal axis, right. And what is principal axis? If you have x, y, z axis, and in those axis system the product of inertia terms are all 0. Okay, you have 9 components of moment of inertia, 3 on the diagonal, which we write I x x, I y y and I z z, and then the off diagonals which we write I x y or I y x or I x z and so on. So, those are product of inertias. So, if you are using the axes which are also principal axis of the rigid body through that origin, then the life is simple in many cases. Okay. So, we will be talking of this. We will be choosing axis system which is fixed with the body and the axes themselves are principal axis. So, then what happens to the equation of motion, this equation of motion. All right. So, in this system, if you have this, we will write it as 1, 2, 3. Suppose this is the origin and then there is some one direction, one axis, then there is some 2 axis and there is some 3 axis. So, this 1, 2, 3 and the unit vectors are E1 cap, E2 cap, E3 cap. These are principal axes of this this body, and for a given body and for a given this origin, you can always find at least one set of principal axes. Okay, you can find more also, then you will have a choice which one you want to use, and those unit vectors are E1 cap, E2 cap, E3 cap. All right. So, this is our tau, this is our torque, inertial frame. Now, what is this? What is this? What is this? In the rotating frame, what is dl dt? In the rotating frame, you will write L as L1 E1 cap, L2 E2 cap and plus L3 E3 cap, and this omega you will write as omega you will write as omega 1 E1 cap plus omega 2 E2 cap plus omega 3 E3 cap. Because in general you will be said, okay, this body is rotating about it has this angular velocity at this instant, and this angular velocity is not, this direction is not a principal axis direction. So, you cannot choose your axis here if you want to use this formulation. Then this omega will have some component in E1 direction, E2 direction and E3 direction. So, it is this, and then this L1 will be I1 omega 1, L1 will be I1 omega 1, that is it. If you are using principal axis, is very simple, L1 is just I1 omega 1 E cap here, E1 cap here, plus L2 is I2 omega 2 E2 cap, and plus L3 is I3 omega 3 E3 cap. Okay. Because in principal axis system you do not have any this off diagonal terms. So, your matrix is like this, Ixx which I am writing I1, Iyy which I am writing I2, and I33, Izz which I am writing I3, and rest are all zeros, rest are all 0. So, if you want to write L, which is I times omega, this is I and this is omega, omega 1, omega 2, omega 3. And then you can see L1 is I1 into omega 1 plus 0 into this plus 0 into that. So, there is just I1 omega 1, and similarly L2 is I2 omega 2 and L3 is I3 omega 3. So, what is this dl dt in the rotating frame? This dl dt in the rotating frame, dl dt in this rotating frame, in this body fixed principal axis frame, that will be I1 will not change. Now, you are fixed with the body, axes are fixed with the body, the x axis or one axis that you have chosen, it is fixed with the body. So, I1 which is Ixx, usual moment of inertia about the one axis, that is not going to change with time, but omega 1, yes, it can. So, it is omega 1 dot E1 cap plus here it is dl dt. So, this is L dl dt I1 and then omega 1 dot E1 cap plus I2 and then omega 2 dot E2 cap and plus I3 and omega 3 dot and IE3 cap. This is this first term. And what is omega cross L? Here is omega, here is L. So, what is omega cross L? So, omega cross L, you can write it E1 here, E2 here, E3 here, cap, 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 and then omega 1, omega 2, omega 3, and this L1, L2 which is I1 omega 1, I2 omega 2 and I3 omega 3. So, the x component, the one component omega cross L, one component will be E1 cap and then omega 2 into this, that is I3 omega 2 omega 3 and minus this into this, minus this into this, I2 omega 2 omega 3. This is just a way to easily write this cross product, otherwise you can always do this omega cross L, that means omega 1 E1 cap cross this whole thing, and then E1 cap cross E1 cap is 0, E1 cap cross E2 cap is E3 cap, E1 cap cross E3 cap is minus E2 cap, and so on. Similarly, do with this term with this term, and you can get the same expression. So, this is the x, this is the first component. So, this is the first component. So, I can remove this, and similarly the second component will be just cyclic permutation of this. You can take this omega 2 omega 3 common, and it is I3 and minus I2, and the second component will be omega 3, in place of 2 you write 3, in place of 3 you write 1. So, omega 1 here, and then in place of 3 you write 1, in place of 2 you write 3. So, it is this. and similarly the third component is omega 1, omega 2 cyclic permutation, I2 and minus I1. This is it. All right. So, now let us write this equation, one component of this equation, one component, take one component, and I am writing 1, 2, 3, not x, y, z, because x, y, z we will be using for inertial frame, and this is the principal axis frame that we are writing. So, we have given different names, not I cap, j cap, k cap. Of course, you can do that, but in many cases you have to use both the frames, inertial frame and this rotating frame. So, that is why we are using these symbols. So, the one component in this direction, that will be tau 1, one component of the torque. So, now we are writing this equation, one component of the torque is equal to one component of dl dt, dl dt is here, one component of dl dt is I1 omega 1 dot. So, this is I1 and omega 1 dot plus, right, one component of omega cross L, and one component of omega cross L is here. So, it is plus omega 2 omega 3 and then I3 minus I2. Then two component along this direction, this principal axis. So, that component will be here, it will be tau 2, inertial frame of reference, dl dt is the torque. So, tau 2 is equal to, and then two component of this is here, I2 omega 2 dot. So, I2 omega 2 dot, and then two component of this is here, omega 3 omega 1 and I1 minus I3. Then similarly tau 3, the three component of this is tau 3, three component of dl dt is I3 omega 3 dot. So, this is I3 omega 3 dot, and then plus three component of this, which is omega 1 omega 2 and I2 and minus I1. In fact, if you have written 1, do a cyclic permutation of these indices and you get this, and do cyclic permutation of this, you get this. So, these are the equations, they are named as Euler's equations. Euler's equation for this rigid body motion. So, if it is easier to use this frame, you can use these equations to describe the motion. So, let us take some examples of using this Euler's equations. So, here is the problem. A uniform rectangular plate is rotated about its diagonal AC, figure is given. So, ABCD is a uniform rectangular plate and this AC is one diagonal with a constant angular velocity omega. So, it rotates about this AC with a constant angular velocity omega. First question is, find the torque needed to maintain this constant angular velocity. You know, even for maintaining uniform constant angular velocity, sometimes you need torques. If the forces to produce this torque are applied at the support points at A and B in directions perpendicular to AC, find the magnitude of these forces. So, if the forces are applied here and here, then you have to find the magnitude. So, let us first do this. Since the axis of rotation is along the diagonal, or the diagonal is the axis of rotation and that is fixed omega. So, we can choose our origin at the center of this plate. So, let us choose our origin at the center of the plate, and then the principal axes are very simple. This is one principal axis, this is another principal axis, and the third is perpendicular to this plate. So, these are the axes. Let us call this as one axis, this as two axis, and this perpendicular to the plate as 3 axis. This is a principal axis, because if you take a plane here, plane of this type, then they say reflection symmetry plane. If you reflect in this plate, or it is a twofold rotation symmetry axis also. So, that also tells me that this is principal axis and this is a reflection symmetry plane. So, any line perpendicular to it will be principal axis. Similarly, this is principal axis and the third one is also principal axis. Okay. So, if I am using these 1, 2, 3 axes and which are principal axis. So, I can write what is I1. I1 is the usual moment of inertia about the first axis. Okay, let us take length as L and width as B. So, moment of inertia about this, moment of inertia of this plate about this line, and that will be m b square by 12, mass of this plate. Let us take this as m. So, I1 is m b square by 12, I2 will be m L square by 12, and I3 perpendicular axis theorem will be m L square plus b square by 12. So, this is I1, I2 and I3, and omega, this is omega direction and the magnitude is omega and that is fixed. So, omega is equal to omega 1, or omega 1 is equal to component in one direction, that is this omega into cos of this angle here, cos of this angle, let us call it theta, let us call this angle as theta. We know what theta is, tan theta is b by L, tan theta is b by L. So, it is known. So, this is cos theta, omega 2 is omega sin theta, because these are in the same plane, this axis and this line are in the same plane. So, omega cos theta this side, omega sin theta that side, and omega 3 is 0. What are our Euler's equation? Tau 1 is equal to I1 omega 1 dot plus omega 2 omega 3 and I3 minus I2. Euler's equation, first equation is this. Then you have second equation is just cyclic permutation, 1 becomes 2, 2 becomes 3, 3 becomes 1, 3 becomes 1 and 2 becomes 3. Then tau 3 is equal to I3 omega 3 dot and plus omega 1 omega 2 I2 here and minus I1 here, 1 becomes 2 and 3 becomes 1. So, these are our Euler equation. Let us use these quantities here. What is tau 1? Let us see what is tau 1. So, tau 1 will be equal to omega 1 dot, omega 1 is omega cos theta, does not change with time, and therefore, this is 0. And omega 2 is also constant. So, this will be 0, omega 3 is constant. So, this will be 0, these terms are 0. Here omega 2 into omega 3, omega 2 into omega 3 is 0, omega 2 into omega 3 is 0. So, tau 1 is 0, we get tau 1 is 0, tau 2, this is anyway 0 and omega 3 is 0. So, this omega 3 is 0 and therefore, tau 2 is also 0, and we are only left with tau 3. This term is 0, omega 3 is constant, omega 3 dot is 0. Here it is omega 1 into omega 2, omega 1 into omega 2, and that is omega square sin theta into cos theta, and then I2 minus I1. So, I2 is here and I1 is here. So, m and then L square minus b square and divided by 12. Okay. You have I2 minus I1, here is I2, here is I1 and I2 minus I1. So, m L square minus b square divided by 12, this is the torque. So, our torque needed is, our torque is equal to omega square. What is sin theta and what is cos theta? So, cos sin theta is b divided by this. So, b divided by square root of L square plus B square, and then cos theta is L divided by the same. So, L divided by square root L square plus B square. So, that is the sin theta cos theta, and then m and L square minus B square by 12. So, this is the torque, this is the torque. You have m, then you have omega square, you have B, you have L, and then you have this quantity L square minus B square by 12, and then divided by L square plus B square, E3 cap, right. So, this is the torque which is needed, and the torque is in the direction of E3, and that direction is changing as it is rotating. Remember that E3 direction is perpendicular to the plane of the plate, and the plate is rotating about this diagonal. So, this plate is rotating, and the normal, the perpendicular is also rotating, this E3 direction is also rotating. E1, E2, everything is rotating. These are body fixed principal axes. So, your torque is not constant, the torque is changing. So, you have to do proper, you have to apply proper forces. Now, the second part is this torque is obtained by applying forces here and perpendicular to AC, and the torque is in A3 direction. So, E3 direction. So, this direction, so it should go like that, and hence this force is here in this direction and here in this direction. They must have equal magnitudes. The center of mass is fixed. So, this is F and this is F, and the torque of these two about this line, this point is F multiplied by this and plus this, the whole length, which is L square plus B square square root of that. Okay, let us see once again. The force of this F, the torque of this F about this, what is that? Since it is already perpendicular, it is F multiplied by this length and in this direction, and here the same thing, F multiplied by this length, same thing, and therefore, F multiplied by double of this length, that means this whole diagonal, and that is L square plus B square square root. So, it is this. So, this should be torque, this should be torque. If I apply F, this is the torque, but what I need this much. So, this is m omega square L B by 12 L square minus B square divided by L square plus B square, and from here you can get F. What is F? F will be m omega square L B by 12 L square minus B square divided by L square plus B square to the power 3 by 2. So, this much force you have to apply here and this much force you have to apply here to get that torque, to maintain this uniform angular velocity of this rectangular plate about the diagonal. Let us take next question. So, here is another problem. A uniform circular disc of radius capital R and mass capital M rests on a support at its center. At time t equal to 0, it is given an angular velocity omega, which makes an angle alpha with a normal to the disc. So, what is the situation? You have a circular disc. So, suppose you have this circular disc, and then at t equal to 0, this is let us say the normal, this is let us say the normal perpendicular, and then it is given an angular velocity omega, which is making an angle alpha with this normal, So, that is the situation. At t equal to 0, this is given in angular velocity omega, which makes angle alpha with this normal to the disc. This is a circular disc and it is supported at the center, and therefore, there is no torque, right. It is just supported at the center. So, weight etc., these things are not important for us, and no torque is applied, and just this angular velocity is given at t equal to 0 and then left. and then your question is find the angular velocity of the plate at a later time in an appropriate frame. So, let us choose a principal axis frame which is fixed in the body, and we choose our 3 axes along this, because this is the principal axis, it is a circular disc. So, any diameter, any radius gives you a principal axis direction, and perpendicular to the disc is also a principal axis direction. So, this is 3, and at t equal to 0 you know what is omega and what is this 3, and in that same plane you draw the radius, and that we will take as our 2 axis, and perpendicular to this 2 axis we take another radius, and that will be our 1 axis. So, this is the radius, this is the radius. So, they are principal axis, this is normal, that this is also principal axis. So, this is our principal axis system. And if I write Euler's equations, remember I1 tau 1 is equal to I1 omega 1 dot plus omega 2 omega 3, then I3 minus I2. This is tau 1, tau 2 is I2 omega 2 dot omega 3 omega 1 I1 minus I3, and tau 3 is equal to I3 omega 3 dot, and then omega 2 omega 1 and omega 2. So, omega 1 omega 2 and then I2 minus I1. So, these are the Euler equations. In our case tau 1, tau 2, tau 3 all are 0, and then let us see what happens. Let us see what happens. What is this? This is 0. So, I1 omega 1 dot is equal to minus omega 2 omega 3 and then I3 minus I2. We know what is I1, I2, I3. Okay. So, let me put I1. What is I1? I1 is moment of inertia of this disc about this one axis, which is a diameter, and it should be mr square by 4, correct. About this normal, it is mr square by 2, and then these two are equal and they add to this one. So, this should be mr square by 4. So, I1 is mr square by 4, I2 is also mr square by 4, and I3 is mr square by 2. So, it gives me I1 which is mr square by 4 omega 1 dot equal to minus omega 2 omega 3, and I3 minus I2, this minus this, which is mr square by 4, and therefore, omega 1 dot is equal to minus omega 2 omega 3. Okay. Similarly, write that second equation, this one, tau 2 is 0. So, 0 is equal to I2 is this one, mr square by 4, and omega 2 dot. So, this is all right. So, this is 0. So, this is negative of that. So, I2 omega 2 dot is equal to minus omega 3 omega 1, and then I1 minus I3. Here is I1 and minus I3 is here. So, minus mr square by 4. So, this is minus mr square by 4. See it once again, what I am doing? I am writing this equation, and tau 2 is 0. So, 0 is equal to this. So, I2 omega 2 dot is negative of omega 3 omega 1 and I1 minus I3, and that is what we are writing. I2 omega 2 dot, this is I2 omega 2 dot is equal to minus omega 3 omega 1. So, minus omega 3 omega 1, and then I1 minus I3, I1 minus I3 is minus mr square by 4, and therefore, if you cancel, you get omega 2 dot is equal to, this becomes plus omega 1 and omega 3. So, omega 2 dot is equal to omega 1 and omega 3. And the third equation is tau 3 is equal to 0. So, this is negative of that. So, I 3 and omega 3 dot, I 3 omega 3 dot is equal to negative of omega 1 omega 2 into I 2 minus I 1, and I 2 and I 1 are equal, and therefore, this is 0. So, this is 0, and hence omega 3 dot is 0 and omega 3 is constant. And what is that constant? What is that constant? That is constant. So, the value does not change with time. At t equal to 0, we know omega 3 is omega cos alpha. So, this constant is omega 3 cos alpha. So, this is it. So, omega 3 is fixed, omega 3 we have gotten, this is omega 3. Look at omega 1 and omega 2, and let me use that same technique I had done earlier, multiply it by I, and this I is square root of minus 1, and add. You get omega 1 dot plus I times omega 2 dot is equal to minus omega 2 omega 3 plus omega 1 omega 3 and I, which is equal to, let us take omega 3 into I as constant, I omega 3 as common. Let us take this as common. From here I get omega 1, and from here I get plus I omega 2, right. You can check. When I multiply this, I get I omega 3 omega 1, which is here, I omega 3 omega 1. When I multiply this, I into I is I square, that is minus 1, and then omega 3 into omega 2. So, here is minus 1 and here is omega 2 into omega 3. So, it is this. So, if I say q, if I name it q, omega 1 plus I omega 2, if I name it q, this is q dot. This is q dot, and is equal to I omega 3, I omega 3, and this is q. So, a quite simple equation, q dot is equal to I omega 3 q, and hence dq divided by q is equal to I omega 3 and dt. Q dot is dq dt, that dt goes this side, I omega 3 dt, this q comes here, dq by q. What I have? I have q dot is equal to I omega 3 and q. So, I am integrating dq divided by this q is equal to I omega 3 dt. So, integrate ln of q, ln of q is equal to initial final omega I omega 3 and then t here 0 to t, this is also from t equal to 0 to t, q ln of q at time t, which I write q, divided by q at time t equal to 0, this is it, and that is equal to I omega 3 t, and hence q is equal to q at the initial time and e to the power I omega 3 t. What is this? What is this q 0? At t equal to 0. At t equal to 0, what is q? Q is defined here. At t equal to 0, I had taken my 2 axes in the plane of omega and this 3 axis. So, these are in one plane and this is perpendicular to that plane, and therefore, this omega has no component in one direction. So, omega 1 is 0. So, at t equal to 0, omega 1 is 0 and omega 2 is omega sin alpha. So, it is omega sin alpha. All right. So, q is equal to omega 1 plus I omega 2 is equal to I omega sine alpha. This is q at t equal to 0. Hence, q at time t is equal to q at time 0, which is I omega sine alpha, and that multiplied by e power I omega 3, and that omega 3, in fact we know omega 3 is omega cos alpha. So, this is omega cos alpha, right. So, this is equal to I omega sine alpha multiplied by cos of omega cos alpha and plus I times sine of omega cos alpha, and that is equal to first let us write this one, this multiplied by this, right. This e to the power I omega cos alpha is cos of omega cos alpha plus I times sine of omega cos alpha. So, this multiplied by this will be minus I is minus, then I have omega here, then I have sine alpha here, and then I have sine of omega cos alpha here. So, it is dimensionally not correct. So, I have left something. So, q is equal to, this is q at time 0 e to the power I omega 3 times t. So, it is omega t here, omega t cos alpha and omega t cos alpha, right, good. So, omega t cos alpha is this minus then omega, then sine alpha, then sine of omega t cos alpha, right. And then this multiplied by this is plus I omega sine alpha and multiplied by cos of that same thing omega t cos alpha. Okay. But what is this q? This q is omega 1 plus I omega 2, and the real part should be equal, the imaginary part should be equal. So, omega 1 should be equal to the real part, and where is the real part? This is the real part. So, omega 1 is minus omega sine alpha and then sine omega t cos alpha or omega cos alpha times t, and omega 2 is equal to, what is omega 2 is that imaginary part, and that is here, this is omega sine alpha times cos of omega t cos alpha. All right. So, we have gotten omega 1 as a function of time, omega 2 as a function of time, and omega 3 as a function of time in the particular principal axis frame we have chosen. So, that completes our question. We have gotten omega as a function of time in this frame. However, what is the, how does the disk look like in the lab frame? Because this tells me that this omega 3 is constant. So, the component of omega about this 3 axis is constant, that is fine, and omega 1 and omega 2 are rotating. Omega 1 and omega 2 they are rotating with this angular frequency omega cos alpha. So, if I look at in this frame, in this principal axis frame, this omega is rotating, it is going in a cone, this omega vector is going in a cone. The tip of this is going in a cone, because in our frame we consider 1, 2, 3, these are the axes, and the entire motion is described in that frame. So, this is 3 axis fixed in our body, and in that frame this omega has to move this way, this has to change, the axis of rotation has to change this way. It is body is rotating about this, then about this, then about this, then about this. So, these vectors are changing with time, and that rotation is this, and this cone is known as body cone. But if you go in the lab frame and there you see what happens. So, even this 3 axis is not fixed, even this is going in a rotating frame, rotating fashion. And how to get that? So, I will just give you some hints. You calculate what is the angular momentum. Okay, you calculate what is the angular momentum, and that angular momentum is fixed in the inertial frame because there is no torque. So, that will have a direction, this L will have a direction, and that is fixed direction, and then this 3 axis will go around that this L vector, and that yet another cone which will be made. So, these are the body cone and the space cone, those are somewhat more advanced topic that I will be not taking up. So, in the next lecture we will take some more problems on rigid body dynamics and see how we solve it.